Good morning, everybody. I am Dr. Rajini Samuel, Associate Professor of Biochemistry, Shri Sathya Medical College and Research Institute, Chennai, India. My research topic is Novel Equations of Motion for Ventilator Graphics Interpretation. Ventilator graphics is an indispensable tool at the bedside for monitoring of the mechanical ventilation. Amid the COVID-19 critical situation, the ventilators play a major role in the management of these patients. Although continuous advancement in mechanical ventilator technology takes place, understanding and interpretation of ventilator graphics at the bedside is considered the most important in management of intensive care unit patients. Equation of motion for respiratory system. The basic mathematical model of breathing mechanics considers the respiratory system as a single compartment model. The parameters like pressure, volume and flow are all continuous functions of time during ventilation. This is known as the equation of motion for the respiratory system or the force balance equation. Total pressure required to inflate the lung is the sum of the pressure required to overcome the airway resistance and the elastance of the respiratory system. In the ventilator graphic display, curve or scalar waveforms and ventilator loops or plots are used to analyze the respiratory system mechanics to provide the information about the patient-ventilator interaction. Air movement takes place between the atmosphere and the alveoli inside the lungs during breathing. This movement is driven by the pressure gradient between these two sides and hindered by airway resistance. The airflow is directly proportional to the pressure difference and inversely proportional to the airway resistance. Airway resistance varies between inspiration and expiration, and it is normal that the expiratory resistance is higher than the inspiratory resistance due to the shape of the airway tree. Compliance denotes the amount of air in ml the lungs can hold for every 1 cm water change in pressure. Elastance is the reciprocal of compliance. Positive N expiratory pressure, PEEP. During expiration, a baseline or expiratory pressure is always measured and set relative to atmospheric pressure, and a positive value is called as the positive end expiratory pressure. This is referred to as a baseline variable. In zero setting, the baseline pressure is set equal to the atmospheric pressure. Volumetric flow rate and mass flow rate. Mass density is equal to mass by volume. Volumetric flow rate is defined as the volume of fluid or gas flowing through a surface per unit time. So Q is equal to dV by dt. It's a time derivative of volume. Mass flow rate is the mass of a substance which passes per unit time. This is the time derivative of mass. So mass flow rate and volume flow rate are related using mass density. Volumetric flow rate can also be defined using dot product of two vectors, namely the flow velocity vector and the cross-sectional vector area. Q is equal to V dot A, so which is equal to V A cos theta. Q depends on the magnitude of the flow velocity vector and the cross-sectional area vector and the cosine of the smallest angle between them. If the angle is 0, maximum volume flows. As the angle increases, lesser volume flows. The volumetric flow rate is 0 if the angle is 90 degree. Relationship of physical quantities. Kinetic energy is equal to half mv square. Acceleration is equal to velocity by time taken. Force is equal to mass into acceleration. Momentum is equal to mass into velocity. Pressure is equal to force by area. Airway resistance in the airway is equal to the pressure gradient divided by the volumetric airflow. Airway resistance is equal to delta P divided by volumetric airflow. Airway resistance, flow and pressure gradient. So resistance is equal to pressure gradient divided by volumetric flow rate, or volumetric flow rate is equal to pressure gradient divided by airway resistance. Another derived relation, resistance is equal to mass density into volumetric flow rate divided by area square. Resistance is inversely related to the square of the cross-sectional area or fourth power of radius. As the density and volume flow rate increases, the resistance also increases. Thus, high flow rate will result in increased resistance, which in turn result in increased peak inspiratory pressure. Relationship between pressure, volume and compliance. So delta V is equal to change in volume in ml. Delta V is equal to change in pressure in centimeter of water. Compliance is equal to delta V divided by delta P. And elastance is the reciprocal of compliance. So elastance is equal to delta P divided by delta V. So pressure volume loop, using this we can compare the compliance, whether it is increased, decreased or normal. Work done is a product of force and displacement, hence it is a scalar quantity. Work done is equal to Fs cos theta. Work done is also the product of pressure and volume. Work is equal to pressure into volume. So product of pressure and volume is the same as the product of force and displacement. So the work required to deliver a tidal breath during inspiration is a product of tidal volume and airway pressure. Work done during breathing is increased by the resistance. These are clearly explained using pressure volume work. Inspiratory time. Inspiratory time is measured from the beginning of the positive flow to the beginning of the negative flow. The positive flow denotes inspiration, the negative flow denotes expiration, because the direction is opposite to inspiration. The inspiratory time is the sum of the inspiratory flow time and the inspiratory pause time. Pause time denotes the flow has ceased, but expiratory flow is not yet allowed. The amount of tidal volume inhaled is a product of inspiratory flow and the inspiratory time. Total cycle time and frequency. Total cycle time or ventilator period is the sum of both the inspiratory time and expiratory time. Frequency denotes the number of breaths or number of ventilator cycles per minute. Total cycle time is inversely related to the frequency. Frequency is equal to 60 seconds divided by total cycle time. Time constant. The change in lung volume during the process of inspiration and expiration is due to the variation in pressure, but it is a time-consuming process. Time constant describes the speed of this process, and it specifies how much time is required to inhale adequate tidal volume during inhalation and to exhale the required tidal volume during expiration. Time constant is defined as the time required for inflation up to 63% of the final volume or deflation by 63%. Static compliance measures the elasticity of the lung when there is no air movement. Time constant is equal to resistance into compliance. Inspiratory time constant is equal to compliance into inspiratory resistance. And expiratory time constant is equal to compliance into expiratory resistance. Thus, inspiratory time constant is shorter than the expiratory time constant because airway resistance is usually lower during inspiration as compared to expiration. Time constant is the time interval. Short time constant imply a faster rate of change and a long time constant imply a slower rate of change. The inspiratory time and expiratory time are to be represented in terms of their time constant. They are calculated ratios, namely inspiratory time divided by inspiratory time constant and expiratory time divided by expiratory time constant, are used to assess the completion of the process of inspiration and expiration respectively. So these ratios will be 5, 4, 3, 2 and 1, and these denote the percentages 99.3, 98.2, 95.1, 86.5 and 63.3 respectively. So the inspiration process will increase by these percentages, the expiration process will decrease by these percentages. Expiratory time constant. The expiratory flow is a passive process, so the ratio between expiratory time and expiratory time constant is very important in assessing the respiratory mechanics. High resistance leads to a long time constant because time constant is equal to resistance into compliance. So long time constant will result in the lung unit fills and empties slowly. Low compliance will result in short time constant. So the lung unit fills and empties quickly. After one time constant or ratio of 1, the expiratory flow will decrease by 63.3% to reach a value of 36.7%. The expiratory flow will decrease by 99.3% to reach a value of 0.7% after 5 time constant. So ratio of 5. So 5 time constant or ratio of 5 is required for adequate exhalation. Inhalation process. Inhalation is an active process that requires resistive work of breathing to overcome the frictional resistance of flow and elastic work of breathing to overcome the elastance of the respiratory system. This is compared to the pressure needed to inflate a balloon. The energy required for inspiration is more than that required for expiration under physiological conditions because only resistive work of breathing is required for expiration. Exhalation process. Tidal breathing during exhalation is a passive process that does not require active energy. The elastic energy stored during inspiration is partly utilized as a resistive work of breathing for expiration and partly dissipated as heat energy. The pressure associated with the delivery of a tidal breath is defined by the simplified equation of motion of the respiratory system. The parameters like pressure, volume and flow are all continuous functions of time. The equation of motion of respiratory mechanics are force balance equation. Total pressure required to inflate the lung is the sum of the pressure required to overcome the airway resistance and the elastance of the respiratory system. So pressure as a function of time is equal to resistance into flow plus elastance into volume. So dV by dt denotes flow and volume as a function of time. Vt denotes the volume. Volume is equal to constant or average flow into time. So this equation is a differential equation and not an algebraic equation. Derivations of equation of motion. At any moment during inspiration, the airway pressure must exactly balance the forces opposing lung and chest wall expansion. The opposing pressures are the sum of the flow resistive pressures, elastic recoil pressure and inertance pressure of the respiratory system. So airway pressure is equal to resistive pressure plus elastic recoil pressure plus inertance pressure. The inertial forces are usually negligible during conventional ventilation. So the inertance pressure can be omitted. So now the equation becomes airway pressure is equal to resistive pressure plus elastic recoil pressure. So airway pressure is the pressure generated either by the ventilator or the muscle. Inspiration is an active process that needs energy for both resistive and elastic work. Resistive pressure gradient is equal to flow into resistance and elastic pressure gradient is equal to elastance into tidal volume. Positive and expiratory pressure PEEP. During expiration, a baseline or expiratory pressure is always measured and set relative to atmospheric pressure. In zero setting, the baseline pressure is set equal to the atmospheric pressure and a positive value is called as the positive end expiratory pressure PEEP. This is referred to as a baseline variable. An increased minute ventilation or any obstruction due to airway resistance may cause an incomplete expiration due to inability in fully exhaling the tidal volume before the next breath. PEEP. If inspiration starts before the end of previous expiration, some air will remain trapped inside the lungs. If allowed to equilibrate by preventing the next breath to happen, the trapped gas volume will generate a positive pressure. This pressure is called as the auto PEEP or intrinsic PEEP because it is not set directly by the clinician. Auto PEEP is present if flow does not reach zero before the beginning of inspiration. Auto PEEP. The pressure generated due to the volume of this trapped air is a product of elastance and residual volume. Auto PEEP is equal to V trap into E. Auto PEEP is also the product of expiratory resistance and residual flow. So auto PEEP is equal to resistance into residual flow. Total PEEP is equal to auto PEEP plus set PEEP. So total PEEP is equal to resistance into residual flow plus set PEEP, where auto PEEP denotes resistance into residual flow. Derivations of equation of motion. In the presence of positive end expiratory pressure, the equation of motion is written as airway pressure is equal to resistive pressure plus elastic recoil pressure plus PEEP. Ventilator will generate a positive pressure and the gas will flow from higher to lower pressure. Muscle will generate a negative pressure at the other end So the gas will flow through the pressure gradient. In the above equation, airway pressure is replaced by ventilator pressure and muscle pressure. So the equation becomes ventilator pressure is equal to resistive pressure plus elastic pressure minus muscle pressure plus PEEP. So muscle pressure with negative sign is written because it creates a negative pressure at the other end. So equation can be rewritten. And finally, airway pressure minus PEEP is equal to resistive pressure plus elastic recoil pressure, or delta P denotes airway pressure minus PEEP. So the pressure generated by the ventilator or the muscle has to increase above the PEEP level for the pressure gradient to develop that helps in flow of gas across the respiratory system. Derivation of inspiratory flow with pressure gradient, elastance and resistance. So from this relation, airway pressure minus PEEP is equal to resistive pressure plus elastic recoil pressure. We have to substitute resistive pressure is equal to flow into resistance, inspiratory flow into resistance, and elastic pressure is equal to elastance into tidal volume. So tidal volume is the product of inspiratory flow and inspirated time. So we'll be getting the result, airway pressure minus PEEP is equal to IF. IF denotes inspiratory flow into the whole bracket R plus E into TI. So total pressure is equal to auto PEEP plus Z PEEP. So previously we discussed auto PEEP is a product of resistance and residual flow. So we have to substitute in this. So we'll be getting the result, delta P is equal to IF into bracket R plus E into TI. You have to close the bracket plus resistance into residual flow. So in the absence of auto PEEP, the residual flow is 0. So equation becomes delta P is equal to IF whole bracket R plus E into TI. You have to close the bracket. So delta P is equal to airway pressure minus set PEEP. In the same relation, you have to substitute the relation between elastance and compliance. So elastance and compliance are inversely related, and C denotes time constant. So if you substitute, we will be getting the result, inspiratory flow is equal to delta P minus R into residual flow, close the bracket, then you have to multiply by compliance, then the entire thing will be divided by inspiratory time constant plus inspirated time. So in the absence of auto PEEP, residual flow is 0. So equation becomes inspiratory flow is equal to delta P into compliance, entire thing divided by inspirated time constant plus inspirated time. So inspiratory flow, resistance and pressure gradient. So in this equation, airway pressure minus PEEP is equal to inspiratory flow into resistance plus elastance and tidal volume. You have to substitute PEEP and then you have to rearrange, and then tidal volume is denoted by delta V. So we will be getting the result, inspiratory flow is equal to 1 by R. R denotes resistance. So 1 by R into bracket delta P minus resistance into residual flow, close the bracket, then minus elastance into delta V. In the absence of auto PEEP, the equation becomes inspiratory flow is equal to 1 by resistance into delta P minus elastance into delta V, where delta P denotes airway pressure minus set PEEP. Inhaled and exhaled tidal volume. Let the end expiratory alveolar volume be denoted by V, and delta V denote the amount of inhaled tidal volume. Then V plus delta V denote end inspiratory alveolar volume, and delta V minus V denote exhaled tidal volume. Let the amount of tidal volume expired during exhalation be denoted by dV. Then delta V minus V is equal to dV. So end expiratory alveolar pressure is a product of end expiratory alveolar volume and elastance. Similarly, end inspiratory alveolar pressure is a product of end inspiratory alveolar volume and elastance. Passive elastic recoil pressure. Expiration is a process that needs energy only for the resistive work, which is provided by the elastic energy stored during inspiration. The required passive elastic recoil pressure is calculated as the difference between end inspiratory alveolar pressure and end expiratory alveolar pressure. So if we substitute, we will be getting the answer, elastic pressure is equal to elastance into delta V, where delta V denotes tidal volume. Equation of motion for expiration. So in this equation, for expiration, the ventilator pressure and muscle pressure are 0. So we'll be getting elastic pressure is equal to minus bracket resistive pressure plus PEEP. In the absence of PEEP, elastic recoil pressure is equal to minus resistive pressure. The energy for the expiratory resistive work is provided by the elastic energy stored during the inspired tidal volume. The negative sign denotes the flow during expiration is in the direction opposite to inspiration. At each moment in time, the pressure necessary to cause expiratory flow is equal to the pressure stored in the lungs due to elastic recoil. So negative sign indicates flow during expiration is in opposite direction. The negative sign can be omitted to compare only the magnitude of the pressure. So if you substitute, we'll be getting the answer. Delta V is equal to resistance into expiratory flow plus PEEP. So PEEP denotes another. Total PEEP is both auto PEEP and set PEEP. You have to substitute in the place. So expiratory flow resistance and pressure gradient. So if you substitute and rearrange, you will be getting the result. Expiratory flow plus residual flow is equal to 1 by resistance into bracket elastance into delta V minus set PEEP. In the absence of auto PEEP, residual flow is 0. So the above equation becomes expiratory flow is equal to 1 by resistance into bracket elastance into delta V minus set PEEP. The expiratory flow is driven by the gradient between alveolar pressure and set PEEP and decreased by resistance. The pressure necessary to cause expiratory flow is provided by the pressure stored in the lungs due to elastic recoil. So E into delta V is equal to resistance into expiratory flow plus auto PEEP plus set PEEP. At the end of expiration, expiratory flow is 0 and the volume will be the resting volume because the inhaled tidal volume delta V is exhaled. So delta V changes to V. V denotes end expiratory alveolar volume. So the above equation is changed as E into V is equal to auto PEEP plus set PEEP. End expiratory alveolar pressure and volume depends on set PEEP and auto PEEP. So auto PEEP is equal to E into V minus set PEEP. Auto PEEP, also known as intrinsic or occult PEEP, is a positive difference between the end expiratory alveolar pressure and the end expiratory airway pressure PEEP set by the clinician. So E is equal to auto PEEP plus set PEEP. Total end expiratory pressure is the sum of the auto PEEP and the extrinsically applied PEEP in the mechanically ventilated patient. In the absence of auto PEEP, the above equation becomes E into V is equal to set PEEP, or V is equal to C into set PEEP, because elastance and compliance are inversely related. Derivation of expiratory time constant. The pressure necessary to cause expiratory flow in the presence of auto PEEP is elastance into delta V is equal to resistance into expiratory flow plus auto PEEP plus set PEEP. So in the place of auto PEEP plus set PEEP, you substitute E into V, you will be getting the result. Expiratory time constant is equal to delta V minus V divided by expiratory flow. So expiratory time constant is the product between resistance and compliance, and elastance and compliance are inversely related. So expiratory time constant is a ratio between exhaled tidal volume and peak expiratory flow, because delta V minus V denotes exhaled tidal volume. The same relation in the place of set PEEP, if we substitute E into V, and the place of auto PEEP, we substitute resistance and residual flow, we will be getting the relation expiratory time constant is equal to delta V minus V divided by expiratory flow plus residual flow. If the residual flow is 0, then expiratory time constant is equal to delta V minus V divided by expiratory flow. Increased resting lung volume. During inspiration, the lung volume increases by the amount of inhaled tidal volume delta V, and then during expiration, the lung volume decreases, reaching the resting volume by the exhaled tidal volume dV at the end of expiration. So delta V minus dV is equal to V, or delta V minus V is equal to dV. So the difference between the inhaled tidal volume and exhaled tidal volume will be the normal resting lung volume. Increased resting lung volume results if the exhaled tidal volume is lower than the inhaled tidal volume. Work done. Work done during inhalation is required to overcome the resistive and elastic elements of the respiratory system. Work done during inhalation is stored as potential energy which is required during exhalation. Elastic energy due to the elastic recoil of the lung is stored as potential energy which provides the necessary pressure required for exhaling the tidal volume. Work done is equal to pressure into change in volume. Total work done during inspiration. Work required to deliver a tidal breath during inspiration is a product of tidal volume denoted as delta V and the airway pressure gradient. So already we derived the relation pressure airway minus ZP is equal to inspiratory flow in the bracket R plus E into Ti. You have to close the bracket plus resistance into residual flow. The R into RF denotes auto peak. So work done is increased in the presence of auto peak generated by the product of residual flow and resistance. Work done during expiration by passive elastic recoil pressure. Passive elastic recoil pressure denoted by elastance into delta V is equal to resistance into expiratory flow plus auto P plus ZP. So if you rearrange, we are getting the relation elastic pressure minus ZP is equal to resistance into in the bracket expiratory flow plus residual flow. So work required to exhale tidal volume during expiration is a product of the amount of tidal volume exhaled and the passive elastic recoil pressure gradient. So elastic work done is equal to resistance into open the bracket expiratory flow plus residual flow, then close the bracket, then you multiply by the exhaled tidal volume denoted by dV. So these are the novel equations, derived equations. So we can remember for the 5 equations, 2 forms I have given, one for the presence of auto peak, another in the absence of auto peak. We can remember only one form in the absence of auto peak. Other thing can be just we can substitute. For the presence of auto peak, you have to substitute delta P by delta P minus resistance and residual flow. Similarly, the expiratory flow should be substituted by expiratory flow plus residual flow. So we can remember only one form. Simple to remember only one form in the absence of auto peak. Other form just you have to substitute. So delta P is equal to inspiratory flow in the bracket resistance plus elastance into inspirated time. And second equation, inspiratory flow is equal to delta P into compliance divided by inspirated time constant plus inspirated time. Third equation, inspiratory flow is equal to 1 by resistance into delta P minus elastance into delta V. Delta V denotes tidal volume. Fourth equation, expiratory flow is equal to 1 by resistance into elastance into delta V minus ZP. And fifth equation, expiratory time constant is equal to delta V minus V divided by expiratory flow. So in the presence of auto P, we have to substitute delta P by delta P minus R into RF. R into RF denotes auto P. And expiratory flow should be substituted by expiratory flow plus residual flow. Set inspiratory rise time. The inspiratory rise time determines the amount of time it takes to reach the desired airway pressure or peak flow rate. It determines the rate at which the ventilator achieves the target pressure in constant pressure mode of ventilation or flow rate in constant flow mode of ventilation. Peak inspiratory pressure or peak inspiratory flow rate is seen at the beginning of the inspiratory cycle depending on the set inspiratory rise time. Then it is constant throughout the inspiratory cycle and it ceases once the preset or target value is achieved. So the relation delta P is equal to inspiratory flow into resistance plus E into Ti, and inspiratory flow is equal to 1 by resistance into delta P minus elastance into delta V. The pressure gradient is decreased by the set PEEP because pressure gradient is equal to airway pressure minus set PEEP. And airway pressure increased above set PEEP is necessary for the inspiratory flow. The inspiratory flow will decrease with increase in resistance. The inspiration starts at the end expiratory alveolar volume denoted by V. The pressure gradient at the start of inspiration is denoted by delta P minus E into V, and the pressure gradient is maximum at this starting point. So peak inspiratory flow is always seen at the beginning of the inspiration due to maximum pressure gradient delta B minus E into V. As the tidal volume is inhaled during inspiration, the pressure gradient decreases. Inspiratory flow ceases if the pressure gradient between these two ends is 0. Delta B is equal to elastance into delta B. Pressure gradient at the end of inspiration will be denoted by delta B minus E into delta V. Inspiratory flow will decrease with increase in resistance. So more inspiratory time is needed to deliver the required volume. If inspiratory flow stops and does not reach baseline with reduced inspiratory time, then the amount of inspired tidal volume will be reduced. Zero flow state will be seen if the inspiratory time is prolonged. So these are clearly shown in the graphs. And pressure gradient is increased by the resistance at the start of inspiration. Then as the inspiratory time increases, it depends mainly on the elastance, the slope of which denotes the stress index in the second portion of the pressure time waveform. So delta B is equal to inspiratory flow into the bracket resistance plus elastance into inspiratory time. So using this relation, we conclude like this. In constant pressure mode of ventilation, the inspiratory flow is directly proportional to the pressure gradient compliance and inversely proportional to the inspiratory resistance, elastance and inspiratory time constant. So inspiratory flow is equal to delta P into compliance C divided by inspiratory time constant plus inspiratory time. So in these graphs, the pressure time waveform, volume time waveform, the decreased compliance and increased resistance are clearly shown. In the increased resistance in the graph, you can compare the first step is increased. The first step in the pressure time waveform is increased, and for the decreased compliance, the second portion, the slope is increased. So this can be explained using the relation delta P is equal to inspiratory flow into in the bracket resistance plus elastance into inspiratory time. And then the flow time waveform also, for the decreased compliance, it is clearly shown the slope will change. And then the flow also will decrease if the compliance is decreased, and in turn the tidal volume will decrease because tidal volume is another depends on the flow. Set P, positive and expiratory pressure, E into V is equal to auto P plus set P, end expiratory alveolar pressure and volume depends on both the externally set PEEP and auto generated PEEP. The set PEEP, positive end expiratory pressure, increases the volume by requirement of alveoli as well as distension of previously open alveoli. If there is no auto PEEP and set PEEP is 0, then end expiratory alveolar pressure will be at the atmospheric pressure level. Passive elastic recoil pressure. The resistive work of expiration is provided by the elastic energy stored during inspiration. The difference between the end inspiratory alveolar pressure V plus delta V into elastance and the end expiratory alveolar pressure V into V will provide the required passive elastic recoil pressure denoted by elastance into delta V. So elastance in delta V is equal to resistance into expiratory flow plus auto P plus set P. So passive expiratory flow is directly proportional to the elastic recoil pressure and inversely proportional to the resistance and compliance. Expiratory flow, peak expiratory flow is seen at the beginning of the expiration due to the maximum pressure gradient. Then as the expiratory time increases, the expiratory flow decreases due to the expired tidal volume that decreases the pressure gradient till it reaches the baseline at the positive end expiratory pressure. So expiratory flow is equal to 1 by resistance into E into delta V minus set P. I told in the presence of auto P, the expiratory flow EF should be substituted by EF plus RF. So we can remove only one equation. For the auto P, just to substitute. So if the resistance is increased, the flow will decrease. So reduced peak expiratory flow and more expiratory time will be required. Auto PEEP. If the expiratory flow stops without reaching the baseline set PEEP due to the reduced expiratory time, then the amount of expired tidal volume will be reduced due to decreased expiratory flow. That increases the residual flow and volume, resulting in air trapping. Auto PEEP is generated due to the product of residual flow and resistance, clearly shown in the graph. Functional residual capacity and end expiratory lung volume. Functional residual capacity is the volume of gas that remains in lungs at the end of expiration, which is the resting state. In the presence of positive end expiratory pressure, PEEP, it is called end expiratory lung volume. FRC is a lung volume measured without PEEP at atmospheric pressure. An increase in end expiratory lung volume results in dynamic hyperinflation, which prevents the respiratory system from returning to its resting end expiratory equilibrium volume between breath cycles. If the expiratory time is insufficient, residual flow will increase, leading to dynamic hyperinflation. Auto PEEP is generated due to the product of residual flow and resistance, or the product of the volume of gas trapped and the elastance. The residual flow and air trapping that generates auto PEEP is independent of frequency unless it alters inspiratory-expiratory ratio, residual flow and expiratory flow. The passive expiratory flow is inversely proportional to the expiratory time constant. The ratio expiratory time and expiratory time constant is important for the expiratory flow to exhale the inhaled tidal volume to prevent trapping. So in the previous slides we showed you 5 time constants. A ratio of 5 is required for complete exhalation. So expiratory time constant is equal to delta V minus V divided by expiratory flow. So in the presence of auto PEEP, expiratory EF should be substituted by EF plus RF. So clearly shown in the graph. Total work done during active inspiration, total pressure required to inflate the lung is the sum of the pressure required to overcome the airway resistance and the elastance of the respiratory system. So airway pressure minus ZPP is equal to inspiratory flow into the bracket resistance plus elastance into inspiratory time, close the bracket, plus resistance into residual flow. So R into RF denotes auto PEEP. Total work done during inspiration includes both resistive and elastic work. So work done is pressure into volume. So we have to multiply by tidal volume denoted by delta V. So work done is decreased by ZP and compliance and increased by inspiratory resistance, elastance, tidal volume and auto PEEP generated due to the residual flow. Work done during passive expiration. Passive elastic recoil pressure is denoted by E into delta V. So work done during passive expiration is provided by the elastic recoil pressure. Elastic energy stored during inspiration is partly utilized as resistive work of breathing for expiration and partly dissipated as heat energy. So elastic work during expiration is increased by the expiratory resistance, auto PEEP due to the residual flow and the amount of exhaled tidal volume. So WEL is equal to resistance into in the bracket expiratory flow plus residual flow, close the bracket, multiplied by dV. dV denotes exhaled tidal volume. Conclusion. The understanding of the relationship of various physical concepts involved in mechanical ventilation is very important for the interpretation of ventilator graphics. These novel equations are to be considered as differential equations and not as algebraic equations because some of the parameters are held constant while the others are variable quantity that changes with changes in other parameters. The application of this novel equation of motion of respiratory mechanics may help in better understanding and interpretation of invaluable ventilator graphics. And these are my references. I thank one and all for giving me this opportunity to present in this international conference. Thank you.